Okay, so now we're going to start analyzing functions. We're going to look at functions that are what are called one-to-one and onto. There are other words for these. And similarly with relations, when a relation has these three properties of reflexive, symmetric, and transitive, it's an equivalence relation. When with functions, when it's one-on-one and onto, it's called bijective. So it's like one-to-one and onto is bijective. Now let's explain what these things do. Now we have these technical definitions, which is a little bit difficult. But similarly with relations, where you draw a digraph and that's how you analyze a relation, with a function you will draw an arrow diagram and analyze the function like that. Okay, but we'll give the technical definition. A function is one-to-one if each element of the range of f occurs in one and only one ordered pair. Now this, what does this mean? It means that it's probably going to be easier to see on the next page, but if you think of a function and say 0 is sent to 0, and suppose 1 is sent to 0 as well. So this is a very, very basic function. Now the range of f is all the things that are hit, and 0 is hit. And if you look at 0 here, there's an element in the range of f that occurs in two ordered pairs. And what that means is that this function is not one-to-one. Now let's draw it. It's going to be a function from 0, 1 to 0, 1, or it doesn't necessarily have to be that, but we'll say it is. So we'll call, let's write down the set. So we've got set containing 0 and 1, set containing 0 and 1, 0, 1, 0, 1, 0, 1. And we have 0 is sent to 0, and we have 1 is also sent to 0. So see here that instead of having one thing sent to one thing, you have two things sent to one. So this is an example of a function that is not one-to-one. A function is onto, and this one's a bit easier to understand. Actually, I'll give you an alternative for one-to-one. Someone came up with is 2-to-2. So a function is 2-to-2 if a pair of distinct elements are sent to a pair of distinct elements. Whereas here you've got two things sent to one. This is 2-to-1. So another word for one-to-one could be 2-to-2. The next one's a bit easier to understand, in my opinion. A function is onto if the range of f, so it's onto if everything is hit. Okay. A function that is both one-to-one and onto is called bijective. Each element y occurs in one and only one ordered pair. So if it's one-to-one, if it's onto, everything is hit. And if it's one-to-one, only one thing hits them. And this is what's called bijective. And what you might call a perfect matching. So let's give an example of one of these. So say, let's take the set containing ABC and the set containing 0, 1, 2. And let's define a function from ABC to 0, 1, 2. Say A is sent to 1, B is sent to 0, and C is sent to 2. Now note, it's one-to-one. You don't have a scenario where two different things are sent to the same thing, so it's one-to-one. And everything is hit, so it's one-to-one, and onto it's bijective. And here I'm kind of saying that in that scenario, you can think of it like a perfect matching. You got everything is paired up. A is paired with 1, B is paired with 0, C is paired with 2. If you've got finite sets, what happens is it has the same number of elements if there's a bijection between them. And with infinite sets, things get really, really weird. And if you want to learn more about that, Google the Hilbert Hotel. Okay. So using arrow diagrams, here we'll look at some examples of things. Okay. Now what I'm going to do, I'm not going to, I'll show you what I want to see if you're drawing an arrow diagram, and then I break my own. No, let's do it. Okay, so let's name all the sets. Let's say go from A to B. Let's say C to D. Let's say E. Oh, I don't want to call my function my thing F, so I'll call it G. h I. So this is going to be 4 different functions. I just want to get I want good practice in terms of labeling your arrow diagrams. So I want to label the sets. So I'll call that G, H, I. And I also want to name the function. So I'll call this one F1, this one F2, this one F3, this one F4. So the first one is supposed to be not onto but 1 to 1. So suppose if I have one, now I won't name these elements, 1, 2, 3, 4, and suppose there's only 1, 2, 3 things here. Now certainly in this scenario there isn't a hope that it can be onto because there's not enough things to hit everything. And remember with a function you're just going to have one arrow coming out of each of them. So we'll make it 1 to 1. Let's say that's sent to that, that's sent to that, and that is sent to that. So this is not onto because this isn't hit. So it's not onto, but it is 1 to 1. And it's funny, the way you're going to think of 1 to 1 is as not 1 to 1. That will slowly make sense. Next one here is not 1 to 1, but it is onto. So say if I have 1, 2, 3, and 2 here. Now there isn't a hope that this isn't that this is 1 to 1 because say this goes here, this goes here, then the last thing will have to hit one of them. So there's not a hope here in this scenario for finite sets where the cardinality of this is bigger than this, that is 1 to 1. So let's have maybe this going there. So this one is not 1 to 1. Let's maybe just label it. So not onto. So here it fails to be 1 to 1, not 1 to 1. But it hits everything, so it is onto. Next one is neither 1 onto or 1 to 1. So we'll need to see it failing there. That's a failure of, that's not 1 to 1. And we can kind of do whatever we want after this. So this bit, it fails to be 1 to 1. It's 2 to 1. So not 1 to 1. And here it fails to be onto because that thing isn't hit. And then finally, bijective. This will have to be 1 to 1 and onto. And certainly if I'm working with finite sets, the cardinality of both sets will have to be the same. In other words, the number of elements. So how about that sent to that, that's sent to that, and that's sent to that. So you got this perfect. It's onto because everything is hit, and it's 1 to 1 because everything is just hit once. So we can tell if a function. So if this is for finite sets, but if you have infinite sets, usually you're going to draw the coordinate graph, and you can analyze. So this will usually be for functions that are from the real numbers to the real numbers, usually, but not exclusively. So for example, if I go back here, we can do horizontal line tests on these to see which of them are functions. Now I need to find one that is definitely a function. I think this one is a function. So if I do the horizontal line test, this will just illustrate it. Well, there's 2 bits of the horizontal, so we'll do the horizontal line test at 6, and let's see at 8. So we'll just illustrate this horizontal line test before we do it. Now, if this hits it twice, we'll draw a little picture of this. This means it's not 1 to 1. We'll draw it over here. We'll draw little elements of this graph. And you see the way this one at 8 doesn't hit anything? That means it's not onto. Not onto. And this hitting twice means not 1 to 1. So if we draw just a tiny section of this graph as an arrow diagram, or this function as an arrow diagram, so remember, all the coordinates on all the points on the coordinate graph of the form input, output. Now this set is called x, x. Now look, we have 3, 6, and 7, 6. So we got the points. 3, 6, and 7, 6. So we have 3 is sent to 6 and 7 is sent to 6. And we call it F1, F2, F3, F4, F5. So you can see with the horizontal line test, if it cuts the coordinate graph more than once, then it's not one-to-one. And then if it doesn't cut it at all, that means there's no point of the form something 8. That means that nothing hits 8. So it's not onto. Okay, so that's just an illustration, because what I'm getting at is that usually the horizontal line test will be for real functions where it's like these curves, but it also works for these things. Okay, so what have we got here? And we'll explain some of that actually again here. A function from a set A to a set B is not one-to-one if any horizontal line y equal to b intersects the graph of f more than once. And it's not onto if any horizontal line fails to intersect the graph of f. Now one thing that's important is that this b be in b and this b be in b. There's no point drawing a horizontal line, say it's 6.5, because these are relations on x, so they're in x times x, so they're from x to x. 6.5 is not in the codomain, so it doesn't matter. Okay, so we'll draw, what do we draw here? So we'll draw something like this. So this might be familiar to you. It's kind of like a quadratic of minus x squared, and we can analyze a minus x squared. Now we'll look more at examples, you know, of specific functions in a much later chapter. Okay, so we're going to look at b line y equal to b1 and y equal to b2. And we're basically going to repeat what we did previously, but there's no harm if you didn't catch it first thing. So let's say this is b1, or y equal to b1, and y equal to b2. So we have, remember, every point on the coordinate graph is of the form input output. So if we call this x1 and this x2, we have x1 b2 and we have x2 b2. And that's what we can say in terms of ordered pairs. I'm just going to look ahead. What are we going to do here? Yeah, we're going to look at arrow diagrams. And then, like, there's no point of the form x b1. So there's nothing going from x to b1, and we've got 2 points, x1 and x2, both going to b2. So I think we're going to look at this in terms of an arrow diagram. Yeah, we're just repeating ourselves. So the first set here is A, second head here is B, and we have to assume that b1 is in fact in the codomain. E, B, what did we call this function? We call it f. So I like you to keep up with the labeling. So we had x1 and x2. Now this is only a little bit of the arrow diagram. Now there's infinitely many inputs. Like there's infinitely many inputs, but we're just going to put in 2. Both produce an output b2. But there's no point that's sent to b1. So we have 2 points. This isn't the color I wanted, but sure, what can we do? But nothing sent to b1. So this is cutting it twice, like this, means not one-to-one, as you can see here. And if it doesn't cut at all, it's not onto, which is just what this thing says up here. Okay. For bijections, every element of B must be mapped to from a unique element of A. So I think So I think what it means is if we're looking at there's probably different ways I can. What am I going to do here? Maybe draw a graph. Okay, I'm just going to be a little bit clever here, and I'm going to take the inputs to be all these numbers. between there and there. Oh, sorry, excuse me. So all numbers between there and there will be the inputs. And all the numbers between here and here can be the outputs, or the space where the outputs live. So it's not going to be a humongous graph. So if the function is bijective, every horizontal line must hit the graph once and only once. And what that tells you actually is there's only two possibilities actually. Either it goes from here, oh, even there that fails, here up to here without dipping. Did it again. Like that, or like that. It can't do anything else, okay? So if it starts, say, up here, it has to hit things underneath, so it has to go down. But if it goes down and it has to hit up here, it has to turn. And if it turns, the horizontal line will hit twice. So it wouldn't be one-to-one. The other possibility, so basically what this means is in this scenario, now it's only a small scenario, but certainly with functions from intervals of the real line to intervals of the real line, they're either increasing or decreasing. They're the only possibilities. So basically what I'm saying, what's the big story with either of these graphs? Horizontal line cuts once and only once if the function is a bijection. Bijection. And remember, bijection is one-to-one and onto. Okay. So that's getting a bit harder. Let's look more kind of about what kind of questions we'd be looking at. So let X be the set ABC and Y be the set DEF. And we have a function from X to Y defined like this. So A is sent to D, B is sent to E, and C is sent to D. Is it one-to-one? Is it onto? Is it bijective? And the way to analyze these things is with arrow diagrams. So let's draw an arrow diagram. Now we will draw a diagram and just kind of show that it's not really much good. So here's X, here's Y, A, B, C. I don't know why I've done them so far apart. A, B, C, D, E, F. You actually can't draw a diagram for this because it's not a relation on a single set, so there's no point drawing a diagram. You can't. So a diagram would have to be X to X. So let's see, A to D, B to E, C to D. Now let's answer the questions. Is it one-to-one? No. Not one-to-one as A and C. Two things. Mapped is language you can use, or sent. Mapped or sent to D. So that's where it fails to be one-to-one. Is it onto? No. F is not hit. And it's now, to be bijective, it has to be both one-to-one and onto. If you want to say it's not bijective, you can say, oh, it's not one-to-one, so it's not bijective. You can say it's not onto, so it's not one-to-one. It's kind of overkill to say, oh, it's not bijective because it's neither one-to-one nor onto. So here we say not onto. And here we're going to say, therefore, either using this or this, both is overkill. It's not bijective. Okay, let's do a coordinate test and do horizontal line tests. So AD is here, BE is here, CD. Do not join up the dots. Now there's only 3 lines to analyze, only the lines in the codomain DEF. So you got, there's a line, there's a line, there's a line. Ignore them. This line, because it cuts twice, implies it's not one-to-one. And this line, because it doesn't cut it at all, implies it's not onto. Okay. Remember, you can always pause these videos. I'm going to try it on. Here's another one. So again, we'll draw, if you want to analyze it for one-to-one answer and bijective, you can look at these things and kind of eyeball them, but it's just going to be easier to draw the arrow diagrams. So here's the set X, and here's the set Y. These were all little f's by me, but I have a little f there as well, so I changed them to big F's. So X, Y, A, B, C, D, E, F, G. And what have we got? We've got A is sent to G. Oh, I also want to put in this F here. Yeah, that'll do. Maybe I don't need an X right, I just write F. So A is sent to G. B is sent to F. And finally, C is sent to D. So here you can see the way you're going to say it's one-to-one is you're going to say it's not one-to-one. You know what I mean? It's kind of weird, isn't it? So is it one-to-one? Yes. One-to-one. How do we say this? Maybe nothing hit more than once. Yeah, that's how we can do it. Nothing hit more than once. I mean, we could draw a coordinate graph and start doing horizontal line tests, but it's just easier with the arrow diagram. Is it onto? No, because E is not hit. Not onto. E is not hit. And specifically because it's not onto, it's not bijective. Okay. What do we got here? So, similar story. How do you analyze this thing? You should draw the arrow diagram. ABC and DE. Set containing ABC. Set containing DE. And call this function little f. Label your sets X and Y. Source target A, B, C. Now before we start, we know this is not going to be one-to-one because there's only there's three things here and there's only two here. Something is going to have to be hit twice. So let's see what it's going to be. We've A is sent to D, B is sent to E, and finally C is also sent to D. So is it one-to-one? No, because D is hit twice. Not one-to-one. D hit twice. And like maybe the thing is, as soon as you find it being not one-to-one or not onto, you can say at that point, rather than looking at answering the other question, you can already say this is not bijective. And everything it is onto because everything is hit. Onto, and you can say as everything is hit. So it's the fancier way. There's different things you could say. Every element of Y is contained in an ordered pair. You could say, so you could say, so other ways of saying this, all elements of Y in an ordered pair. And that's a bit messy actually. Which is the same as saying everything is hit. And you could actually say, I think the range of F, all the things that are hit, is equal to the codomain. That'd be another way of saying it. I think it's just easy to say everything is hit. Okay, let's see. So we've got, this is an exam question. So we've got a set of inputs here, a set of place where the outputs live. Define a function from here to here using this formula. So the output is the input squared minus 2. List the ordered pairs. So we're going to calculate some of these outputs. So f of minus 1, you gotta be careful there, is minus 1 squared minus 2. Now be careful here, minus 1 squared is minus 1 by minus 1, which is plus 1, and 1 minus 2. Now this will be in the third assessment, and there will be a bit of algebra that you'll have, so there's some, you know, if you're giving out, oh, I don't know the algebra, well, we're going to learn about it. So this is going to be minus 1. Let's input 0. You get 0 squared, which is 0, minus 2 is minus 2. And then input 1. So we put 1 into this, you get 1 squared is 1, minus 2, 1 minus 2 is minus 1, and finally input 2. You get 2 squared, which is 4, minus 2, which is 2. So the ordered pairs f is equal to input minus 1, output minus 1, input 0, output minus 2, input 1, output minus 1, and input 2, output 2. Now if you want, as I said, you can analyze at this point. I know this isn't one-to-one because this appears in more than one ordered pair, and I know that it's not onto because 1 doesn't appear, but it's just going to be easier with an arrow diagram. So that's list the ordered pairs done, and this is how you write it. F is equal to set of ordered pairs, input, output, and then is it one-to-one, is it onto? We'll analyze it using the arrow diagram. Now we've got a big massive space here for an arrow diagram, probably unnecessary. So X and Y. Now if you want, maybe I may as well do it, we might analyze it also using a coordinate graph. Should have the time. I might run out of time, but that won't be the end of the world. So the video might run out of space. So the function is called f, and we have minus 1, 0, 1, 2, minus 1, 0, 1, 2, and then the codomain is minus 2, minus 1, 1, 2. Now one thing people might do is they might list these numbers and repeat minus 1. That shouldn't happen. We shouldn't have an element of a set appearing twice. So using this, minus 1 is sent to minus 1, 0 is sent to minus 2, 1 is sent to minus 1, and 2 is sent to 2. So now answer the question, is it one-to-one? We're going to say no, because minus 1 is hit twice. Not 1-to-1, minus 1 hit twice. That's not onto because 1 is not hit. Plus 1 not hit. And so that's the whole exam question done. Now there's one small thing here. It didn't ask about bijective, but it's not bijective. Let's do the coordinate graph. What would that look like? Be kind of weird actually, because we've kind of got holes all over it. So we have minus 1, 0, 1, 2, the inputs, and then the outputs are, or the place where the outputs live, minus 2, minus 1, 1, 2. Now let's draw all the points. So you got minus 1 is sent to minus 1. We have 0 is sent to minus 2. 1 is sent to minus 1, and 2 is sent to 2. And the two horizontal lines, that one, this one here shows that it's not one-to-one because it hits the graph twice. You do not join the dots, by the way. And the one at x equals y equals 1 shows that it's not onto. So this one doesn't cut, not onto. This one cuts twice, not one-to-one. You do not look at 1.5 or a half because it's not an element of the codomain.